All right, so today we're going to be talking about light. And, we all know what light is, but how are we going to actually light our scene using a shader? But before we do that, let's just back up and explain a little bit, take stock of what we've done so far in this course. So in lesson 1, we made a mesh, which was a simple quad. In lesson 2, then we used that mesh in order to learn about shaders, and we could draw that mesh using those shaders. Now in lesson 3 and 4, we then started doing more advanced modeling and made a 3D model. And so now we can actually take that 3D model and start doing different types of shaders, sort of more interesting shaders to draw that 3D model because we have more interesting geometry to work with. So the type of shader we can do is light. So there's all kinds of different ways that you can represent light in computer graphics. I would sort of generally place those into two different categories. There's going to be direct light and indirect light. Okay, and so let's explain a little bit what I mean as far as these two different terms. And we're going to do some illustrations here. And just for this special lesson here, since we're talking about light, let's go into a dark mode and start drawing the actual light. So let's draw a little scene here. And we're going to be drawing, this is going to be an unlit scene to start out with. So we'll make it sort of in this dark gray. And we're going to be lighting a table. So we have this table here. And this table is going to be lit by a source that's above it as kind of this sun-like or light bulb or whatever source here. And so if you think about what happens in the real world, what happens with this is that light particles, photons, come off of a light source. So they'll shoot off of this light source and they'll strike the table. So you'll see these impacts, and then that will reflect off. And this will be happening in all the different ways. There's going to be tons of these different particles intersecting with this geometry and bouncing all over the place. Okay, and some of these photons will be intersecting and traveling into our eye. And we see that those photons have bounced off of a surface, and that's how we're actually able to see the world around us, is that we're seeing these light particles interacting with a surface, and we can use that to determine, okay, there's actually a surface here, because we'll see all these different impacts, and we'll understand that there's this sort of flat surface here because all the light is bouncing off of it in a particular way. Okay, and so this is what I mean by direct light, is that the photon is coming from the light source, hitting a surface, it's lighting that surface, and then our eye sees that. But I mean, if you even just abstract away this idea of them traveling to the eye, right? Basically, just see, if your eye's in this scene, you'll see that this surface is being lit by this light source. The indirect example is where you start taking into account the bouncing of the light beyond just the direct light source. So think about this being inside of a room. Okay, so we've got some walls here that are sort of situated like that. So we're inside of this room, and you can see I drew a light ray going off that way, a photon going off that way. So that light is actually hitting this table first. It's directly lighting this table, but then it's bouncing off and it's hitting this wall. So this is a bounced light indirectly lighting this wall, though we'll also get direct light hitting it too. But then not only will it bounce off the table and hit the wall, then it will bounce off and hit this floor, right? So we'll see these particles kind of careening all over the place in this indirect lighting. And if you look around in the room around you, that's what you're going to see in real life, right? Is that you're not going to see these black shadows where nothing's being hit by light. You're going to see indirect light bouncing everywhere and sort of generally illuminating the room that you're in. So that's why you can see, let's say, for example, under a table where there's no direct light hitting that, because the table top is being hit. The table bottom is not going to be hit by that at all, but it may be hit by a light that's bouncing off of the floor, right? If we take this idea even further, we can introduce the idea of color, and we can say, actually, this is a red table. Why do we see it as red? That's because that this white light that I've been drawing as white actually contains all of these different colors as part of the electromagnetic spectrum, right? It contains every single frequency of visible light, and that's all going to be emanating off of this light source. And so all that light's coming down, and then this table, which we perceive as red, is actually going to absorb every single one of these frequencies except red. And the red it's going to almost reject, and that's going to be what's bouncing off of the table, and that's what hits our eye, is just this red frequency. So in some way, this table is anything but red that we perceive as red, which is just kind of a weird way of thinking about it. But that will also lead to this red light bouncing off of a surface around it as an indirect light source. So we can see, even though if, let's say this wall is a white wall, we'll actually see little pools of red light reflected on that white wall if we're close enough to it. So that's the idea of indirect lighting. Now in this lesson, we're going to be focusing more on direct lighting because that's just really simple from an implementation standpoint. So let's kind of break this down a little bit and say, what are some common ways that we can represent as sort of like a useful abstraction direct light in our scene? So you've probably seen some of these concepts before. One would be a point light. So that's kind of what I've drawn here, is that you're almost going to have something that looks like a sun or like a light bulb, and it's going to be a light source that's positioned in your scene. It has a specific position in the scene, and the light's going to emanate off of that position in all directions. So just what I just drew already. Then you can have a spotlight. Now the spotlight is actually really similar to the point light. It's almost the exact same thing, except that you can almost think of there being like a light fixture around that point light that's going to block the light from emanating in every direction. It's only going to be allowed essentially to emanate from a specific vector, which is like the forward vector of that spotlight, but it's still positioned somewhere in the scene. So it actually is basically the same exact thing as the point light with an extra constraint to it. Now the third type you'll see commonly is a little bit different. This is the directional light, and you'll see this commonly used in exterior scenes. And the idea here is that rather than being positioned in a scene somewhere, it has no position. It just has a direction. Every object in our scene is going to be lit by that same direction. So no matter if you're sort of like 1 inch away or 1 mile away, you'll still be lit by the exact same light direction. And as I said, this is common in an exterior scene, but I just drew the point light as something that looks like the sun. So why wouldn't you use a point light to represent the sun? Because you can think about the sun has a position to it. So why would that not be a point light? Well, you can just think about the scale of what we're talking about. If we drew the sun way over here, and the sun's going to be here shining, where's our scene going to be? It's going to be way over here, but not even close to it's going to be way further than that. And then we can draw it as this dot, but it's going to be way tinier than this dot here. And so this distance is essentially, as far as the reference of our scene, this distance to the sun is going to be essentially like infinite. It's going to be way bigger than we can represent with the floating point math that our computer has available in the scale of the scene, right? And so what we can say is, rather than representing this as a position, a point light, we can just sort of abstract that further and say the light will just be coming from a specific direction. Now that we've understood these kind of basic common light types when we're talking about direct light, let's try to start modeling this and see how we do this in a shader. So, and let's draw our table again here. Okay, so we've got our table, and then we'll have our light source is kind of positioned up here. Okay, so as we were saying up here, and let's look back at this example, we said the bottom of the table is not going to be lit unless you go into this indirect lighting thing, right? Then it will get light hitting it. But in this scene, we're just seeing the tabletop being lit, and that's because this light source is above the tabletop, so that's getting hit by the direct light. Okay, so how would we translate that idea into code? So basically we can say it has to be above this surface. Well, why is that? And here I'll introduce a concept that you've sort of seen already, which is called the surface normal. And so because this table is sort of, we've already established that it kind of has this red color affiliated with it at least, we'll put this in red, we'll say the surface normal is going to be a new concept we're introducing. It's basically this facing vector of any surface. And so I drew it in the center of the table over there, but it's really going to be for this entire surface. There's going to be this facing vector that shows which orientation that this table has. And in this case, it's going to be the up vector, right? It's pointing up. And as I said before, we've sort of seen this before when we worked with triangles, and we had to specify what the winding order of the triangle was so that we knew which direction it was facing. So we sort of implicitly already worked with this because we saw that if we wound the triangles in a clockwise orientation, it would be facing one way. And if we used a counterclockwise orientation, it'd be facing sort of another way, right? So we already sort of used that, but now we're just making that explicit. We're saying this is called the surface normal of that triangle. Okay, so if we want to determine whether any of these particular points, which we know the surface normal of, is being hit by this light, we have to determine what is the direction that points from this position to the light. So if we look at that, right, or that, we'll see that we have all these different sort of vectors that are pointing to the light source. And as we get further away from this light source, they'll become sort of more pointing to the right direction. But in all these cases, though, they're sort of still pointing up, right? So we can say that we have this vector that's pointing to the light in this way. And what we want to do is calculate what is this alignment, the level of alignment between this surface normal and the vector that's pointing to the light. Because if you see here, if we sort of keep going with this, and let's say we move this light source over here, and so let's say that this is pointing directly at the edge of this table, and let's, rather than saying which direction the light's pointing, we'll see what's the direction pointing to the light. So I drew this light with a radius, but as a point light, it really is just a single point. So if the light's just coming from a single point and it's aligned with the edge of this table, that means that the top of the table is not going to get any light because it's basically 90 degrees away from it. And then if we keep rotating this light down and we say it's coming from the bottom, right, the tabletop is obviously not going to get any light at all because the bottom is going to be lit by the light. And so there, the vector that points to this light is going to be totally unaligned with this surface normal. And so if we look at the alignment between our vector that points from our surface normal, which I'll fill in a second, to the light, right, this alignment is going to tell us how much that we're being lit. All right, so let me just move this over a little bit. And let's just say our lit amount, let's just put that in a different color here. Our lit amount is going to be basically equal to our alignment, though it's not exactly, and that's why I'm putting in a different color. So we'll see in a second. So we'll say if there's a 0 degree difference between the normal and our to light vector, 0 degrees difference, that's going to equal, as far as alignment goes, 100% alignment. And that's going to also equal a 100% lit amount. Okay. Now if we come down to this example, that's going to be like a 90 degree difference. And we'll say that our alignment amount, at this point, we want it to be 0. And that's going to translate to a 0% lit amount as well. Okay, so far these are the exact same thing. Now if we come down here, though, we're going to have 180 degrees. And this is going to be like a negative 100% alignment. But as far as lighting amount goes, you can't go anything below 0 degrees, or 0% rather. So this is going to be also 0% lit. Okay, so what does that describe? If you're familiar with a dot product, that's going to be exactly what this alignment function is describing. Is we're going to have our dot between our normal and our to light vectors will give us this alignment function. And then we're going to want to have some clamp here that takes this and gets rid of these negative values. So we'll put this in a box here. This is the answer that we're going to be trying to put into our shader code. Okay, and then we also want to add an additional constraint here. We want to say where length equals 1 for our n and l. Because if we don't do that, then this is not going to give us this range that goes from 1 to -1. We'll get a different range from this dot product. Okay, and so before we dive into Unity, quick little math diversion here, because this sounds exactly like something we did in our parametric modeling series. It sounds exactly like the unit circle, which again was sort of oriented like this, and we went from 0 degrees to 90 degrees, 180 degrees, 270, back to 0, or 360, right? And what was, as we did this rotation, what went from 1 to 0 to -1 to 0 again, back to 1? That was going to be the cosine of theta, which was our x coordinate that we used for our parametric modeling. So cosine of this angle is going to give us this exact value here, where length equals 1. And remember, our unit circle was also all these lengths were equal to 1, was another little bonus there. So that's another way you can think of this operation we're about to do. So without further ado, I know everyone wants to see the light, so let's dive into Unity and let's start getting that working. All right, so we're back in Unity and we're in our tube scene, which is maybe not correctly named now that we have this pawn here. So let's actually just save this scene here, and we'll save this as new scene, and we'll say our light scene is the name of this scene. And let's change this. This is still just called game object, so we'll call this a pawn. And let's save that. Let's start off by making a new shader. And we're going to just create this. And we'll use a URP unlit shader still because we don't want to use Unity's lights. We want to just make our own light. We'll call this a PFX lit surface. And so then we'll come in here and we'll create a material that goes along with that. PFX lit, we can call it. And to assign the shader, what we can also do, which we haven't done in the previous ones, we just drag that shader over here. And you'll see here it says custom PFX lit surface, so that worked. And now let's drag that to our model. You can see it turned white because we have this white base color assigned to this material. So now let's open this shader here. We can go full screen for a second here. Let's just delete out all of the stuff that references this texture base map and in the UV coordinates, because we're not going to be doing anything with that. So let's just kind of get rid of some clutter here in the shader. So we'll get rid of anything that references this texture, and we'll just make sure that still compiles. Okay, so now let's come back and bring up our cheat sheet here. So the first thing we need to do is we need to look at this concept that we introduced of this surface normal, and we need to make sure that we can have visibility of this surface normal in our shader code. Because right now we just see as far as our attributes. And remember, we rename these things. We're not going to rename them every time, but I just renamed them in the first lesson for clarity. This is going to be coming from our vertex itself, and then this is going to be the output from our vertex shader that then goes into our pixel shader or fragment shader. So our attributes, we want to not only get the position object space from our mesh, we also want to get the mesh's normal. And so what we need to do for that is we can say normal OS is coming from our normal semantic, and Unity will understand what that means. And so then to make sure that we're getting that correctly, let's, rather than using this base color here in our pixel shader, let's specify what the pixel shader's color will be as part of the output of our vertex shader. So we'll just say in the vertex shader, we'll say, okay, just pass this through, and then the pixel shader just draw this color. So we'll add a color to our vertex shader output here. And there is a color semantic we can use there. And we'll say output.color equals our input normal OS XYZ. And then we'll just make sure that it has an alpha of 1. And actually what we could do here is just say out.color.alpha is always going to be 1 there. And then here we can just return our input color and just pass that through. Okay, so let's see, come back here and see. Okay, so that did something. We're seeing some kind of color come through now, but it's just all this blue color. And we're not seeing the individual facing vectors of all these different surfaces, which our 3D mesh should have. So why is that? It's because, again, the last time we tried to do something like this, we had a similar problem, was that as we're building this mesh, we're not actually specifying what the normals are going to be that are attached to this mesh. We saw something similar with the texture coordinates in the second lesson. So, okay, we have to go back into this mesh and go through this whole modeling thing again to add normals. Well, no, because as I said in our cheat sheet here, we sort of already provided this information with the winding orders of these triangles. So because we specified the facing vectors, or surface normals essentially, of all the triangles in our model already. So what Unity is going to be able to do is to take this information that we already provided as far as the winding orders, and we can just come in here and say mesh dot, let's see, there we go, recalculate normals. And let's let that compile. And then let's come into our pawn here and build a mesh again. And then something happened. Oh yeah. So we're now seeing, I mean, this is almost looking like it's lit because all of the various orientations of these surfaces are going to be rendering differently now. And I mean, it's a crazy type of lighting, if you want to call it that. If you notice here, like look at these coordinates, when we point up in the Y direction, we see the same color here, green, as we see on the mesh, and we point in Z direction, we see blue. And then over here we see red when it's pointing in the X direction, because these channels correspond to the first channel, second channel, third channel, not only in the position, but also in the color channels. So the unity orientation here is going to match what we're seeing here, which is kind of cool. But we don't really want to visualize normals. Now that we know that the normals are there, okay, we want to now add some light. Let's actually do something that's like a directional light. Just as a test, we'll kind of hard code something where we can just say the light's going to be coming from a specific direction. So we can just say that the light, the direction to the light is going to be, let's just say that. Okay, so it's going to be pointing up, but then it's also going to be pointing in the positive X and positive Z, just so it's sort of like a tilted angle. We get a little bit more dramatic light that way. And now, if you remember, this has to be a length of 1. Well, this length is going to be greater than 1, because every channel has a 1 in it now. So what we can say is to light equals normalize to light, and that will transform this to a 1 length vector. Now, this normalize, is that the same thing as this surface normal? No, totally different. So it's confusing etymology, which is why I wanted to just use this length 1 as I was explaining it. Let's just try to move past that, but that is something to just make sure that you understand what normalize means versus surface normal. It's two totally different concepts. All right, but we've got our vector that's pointing to the light. This is going to be kind of hard-coded. And so what we can say is our lit amount is going to be our dot between our to light and our normal. Okay, and then here, what we can do is, rather than looking at the normal directly, we can just look at our lit amount. And if you take a single channel float here and assign it to a vector in HLSL, what will happen is that it will assign every channel of this color to this single float value, which can be handy. We're going to create kind of like a grayscale here. And then it's also going to assign the alpha channel to that, though. So that's good that we have this alpha. We want to keep that there to make sure that alpha is 1. So let's come back here and we can see, okay, this is looking like it's a lit surface now. So that's pretty cool. And we're seeing it kind of coming from this positive Z and positive X directions, as well as from the upward direction. And if we kind of reduce these, we can see this should just be coming straight down, right? Let's see here. Yes, so now it's coming straight down. Doesn't really look as interesting, but we can verify that our lighting calculations being done correctly here. Okay, but this is kind of boring. So what we want to do is let's, as in our little cheat sheet here, let's focus on something that's like a point light. So let's add like a script to our scene that will act as a point light. So let's come in here. Let's add a new mono behavior. And we'll call this a PFX light. Rather than calling it a light, because there's already a component in Unity that's called light. So let's just call that PFX light. And let's make sure this executes always, which means we don't have to go into play mode to see this take effect for the update loop, which we want to keep in this. And so in our update loop, let's say shader.setGlobalVector, and that's going to, we'll say light position, and let's set that to our transform.position of this object. And what that's going to do is any shader in our project that has a variable called light position, it will set this value on that shader variable. And so let's make sure our shader has that. So if you come down here, here's our per material variable, but this is not going to be per material. This is going to be on every object that has access to this global variable. So let's put it down here. We'll say light position is here. And so now what we want to do is, now this is going to be a global space position, right? Because if you came back here, we're using not local position, but we're using the world position of this light. So this light position is going to be located in our world space. But if you look at here, the position we're looking at is going to be our object space. So in order to determine our to light vector, what we need to do is calculate what is our world space position. And then in order to get the alignment from our to light vector, which is now going to be in world space, we're going to need to also transform our normal that's in object space into world space as well. So in order to do that, we'll say WSPOS equals mul unity object to world. And then we'll do it this way. in position OS XYZ 1. So what this does is it takes a matrix, in this case the object to world matrix, and it will multiply a vector by that matrix to transform it. And here I'm giving it this sort of float for constructor to say one component in the W channel will make sure that translation occurs, which is basically moving this object around. If this pawn moves, right? If this pawn moves, then that will make sure that transform kicks in. Whereas when I do my transform on my normal, I don't want translation to occur because this is just going to be rotation. The vector that's pointing off of the surface is not a position, it's just a direction. So I want to get rid of that, and I want to make this my normal OS. So now we've got these world space positions and normals. Now I can say my vector to the light is going to be, let's make sure we normalize this, but we'll say our light position minus WS pos will give us our vector to the light. And the reason we're subtracting out our world space position is that this is just like a common way you can get the vector that points in any direction is you take the thing you want to point to and you subtract out the from. Okay? And just a simple way of thinking about this, really simple, is just think about a single number. Is if you, let's say I want to point to 10 from 5, well, that's going to equal 5. Well, that's going to be a positive number. So if you want to point to 10 from 5, you're going to be going in a positive direction, right? Whereas if you point to 5 minus 10, that's going to give you a negative number, pointing you towards the negative vector. So you can use that as a handy sort of shortcut in your mind to remember how you're going to do this pointing operation with vectors. Okay, so I've got my vector that's pointing to my light here, and it's going to be normalized. And so now all I need to do to calculate my lit amount, I'm not going to do the dot product with the object space normal. I'm going to now put my world space normal here, and maybe we can just move this down because we don't need it until we do that. So let's now see what this does. And okay, we've got something changed, but I mean, I don't know if that looks great. The reason because we need to add this light to the scene, right? It's not doing anything yet. So we need to add a light to the scene. Let's just zero this out here, and let's add our PFX light. Okay, still not seeing anything, but if we start moving this, look at that. That's looking pretty good. So now we have our own custom light, 100% custom, that we've added through shaders. And we're lighting our 100% custom pawn mesh here. So that's feeling pretty good. And now if we wanted to take this further, I mean, we're not going to take this super far here, but if we wanted to take this further, we could say, we could add like a color to this light, and we could, set that in our shader, set global color. Okay, we could set the color, come back into our shader, give that a color. And so then what we could do here is we just multiply our color in that way. And so now we're not seeing anything, but if we move this color, now we can give this light a color. So we can make it kind of this like yellowish color, let's say. Okay, so that looks pretty good. But then our shadow is this like pitch black shadow, which I mean, could look cool, but let's say we wanted to give our shadow a color. We could just do the same thing here. Let's do it in the script first. So we could add a shadow color, and let's add our shadow color. Okay. And then we'll come over into our shader. Let's make sure that has a shadow color as well. And so now rather than multiplying our lit amount into our light color, what we can say is we can interpolate between our shadow color and our light color by our light amount, our lit amount. Okay? So we come over here, that still looks the same because we have black as our shadow color. So now if we go in here and maybe add like a blue color, we can start seeing something that looks kind of a little bit more dramatic lighting here. So I think that looks pretty cool. And as you can see, we're not just adding the shadow color in and then adding the light color on top of that if it's lit. We're not seeing any of the shadow color in these lit areas. So we could go like really saturated with these, and we won't see any sort of contamination of the yellow getting into the blue areas or the blue getting into the yellow areas. Let's just make that a little bit less garish, right? Let's bring it back to kind of something that was more like what we had before. Okay, and then we can make this maybe a little bit more cyan like that. So you can see that we really barely scratched the surface, even with these different light types, but obviously there's direct light, indirect light, all kinds of things you can do. And I would recommend looking at not only other real-time lighting sources, but other sources that you could get inspiration from, like cinematography, fine art. There's plenty of resources that talk about the ways that you could light a scene. And you could create your own custom shader that integrates some of those concepts that don't necessarily actually use these simplifications per se. We're going to go a little bit more in this direction in the next lesson, where we're going to learn about shadow. But beyond that, we're going to start moving into other things like animation, simulation. But just be aware, there's all types of things that you could do beyond just what we've talked about here. We're just scratching the surface. So anyway, I'll see you in the next lesson where we talk about shadow.